All right. Well, welcome back. We can definitely get started. I had promised more of the material on FPGA-based design, where we had just started it on Friday. Had some technology issues along the way. I'm going to push that to this upcoming Friday because, as a couple of you noticed, there was a question on the homework that did require that we cover this next topic first for it to make some sense. Now, I think that's okay either way. If there's a question on the homework and we haven't covered the topic, that's where you can ask questions. That's where you can read ahead. That's where you can try it yourself. But I do feel better when there's a homework question and we've actually touched upon it in class so that it doesn't seem like it's completely disconnected from what we are doing in class. And what we're doing in class is really moving into the more quote unquote architectural elements of the course. Certainly the microarchitecture that we're trying to understand in the lab, trying to understand what that means in practice, what are the design trade-offs involved with that. And so there is, after we've finished this performance topic, one other, I'll call it a mini topic, although it all relates. It's specifically about the ALU design for MIPS. What are the basic arithmetic operations that are being supported and how we build them? And this is an interesting topic, I think, in the sense that for many of you, this will seem very easy. Oh, yes, we covered all of this in 281. There's nothing new here. This is really simple and boring. That's fine if that's how you feel. For others, 281 may have been a blur, and it may have been a blur of many semesters ago. And you really do need this topic to understand what's happening. The textbook does an okay job of covering the ALU design. And unlike some other aspects that we are going to be implementing in lab, we are going to essentially just be implementing the textbook design. So there, unlike for the next parts of the project where you can start with the assumption that we're working on the textbook design, but we are changing it significantly. For this one, if you were to take the textbook design and just implement, make that your schematic, you're going to be in okay shape for this assignment in the lab that you're currently working on. It's covered in a couple of different places. In the beginning of chapter 3, it starts to talk about what operations are needed, but it really the textbook pushes all the main low level logic implementation aspects to the appendix, which you may have in your book, you may have as an online supplement, but it does cover the material that we are talking about this week. And as you know, in the lab, you're working on your team based projects, and there's also a bonus criteria for that project part A that is very doable. It sounds scary when you look at it, just like that one homework question for homework 5 sounds kind of scary because we haven't covered it. By Wednesday, if not before then, I will make sure we've covered enough that you'd feel comfortable, starting it and attacking that problem. And for those of you who maybe struggled early in the semester on your labs, that's an easy way to get some points back and kind of get back to where you feel you're really, dominating the labs this semester. But otherwise, this is week 7 of the semester, so we're really at that halfway point. And I do feel if you're here, you've made it this far, you're doing great. And let's just keep on trucking, and it's going to be just fine. And semester is going to go by in a blur, and it's already happening. But everything's aligning a bit more now, and I think it's going to work a little bit better for many of you as opposed to really that crash course on assembly simultaneous with a crash course on VHDL. I promise no difficult math this semester, and that is still the case. So this is very much just a refresher of our grade school math. And the takeaway from this is that when we're worrying about building an adder and building an ALU, the math is no different from our elementary school math. We're dealing with ones and zeros, and so in a sense, it's easier even. But the twos complement representation allows the very basic kind of bit serial approach that I think all of us, if not all of us, most of us would have learned in elementary school, allows it to just directly apply to building circuits to do addition and subtraction with carrying and borrowing of the one. So I won't even go through this example and show what the math works out to be. But if we want to add this value, and this would be 7 plus 6 for, let's say this is an unsigned value here, we would take 1 plus 0, get a 1 with 0 carry. 1 plus 1 plus 0 is 1 with no carry. 1 plus 1 is 0 with a carry. 1 plus 1 plus 1 is 1 with a carry. And then we get 1 plus 0 is a 1 with no carry. So we wind up adding 7 plus 6, and we wind up getting 1101 or 13 back out. So the math does work as expected. And we've covered even from a very early week in the semester that if we want to handle subtraction, one approach is just to treat that subtraction as addition of the equivalent negative number. So there's that inversion or that complement we take of the B input to our ALU, and we're doing that so that we can still use what's effectively an adder circuit and not have a separate adder versus a subtractor circuit and treat everything as if it's an addition. We just then have to be a lot more conscious of what our sign bit is doing and understanding that now if we have that two's complement representation, that most significant bit has special meaning. It represents the negative power of 2 of that MSB versus just an entirely unsigned representation. I made a separate video talking about overflow, and the textbook does cover it as well, and that's posted as the sort of the pre-lab for the lab you're working on currently. We have to be a little bit careful with regards to how we use that term. Some students told me they already implemented overflow, and then I looked at a couple of designs, but not all of them. So I'm not saying everyone did this wrong, and they just took the final carry out as being overflow, and that's not really correct. And I do encourage you to look at that separate video, which is what does it mean to overflow? It means the result is wrong. And how can we relatively easily determine that a result is wrong? And we can do so based on our understanding of what the signs of our inputs, our two inputs, and what the sign is of our result, and how that can potentially happen. And this example is just showing that if this is a 4-bit two's complement representation for our addition, that we're adding 7 plus 1, we actually get a result that's negative 8 back out. That's different from there being a final carry out. It's a result that if we had an additional bit would have been sufficient to store it correctly, but we don't. We're keeping everything to 32 bits or 4 bits in this example here, and the result's wrong. And that's why overflow is something that we have to watch out for. I've got a lot of questions about that because I have talked a lot about there being, um, those two different categories of arithmetic instructions, and I think we've covered it well enough for add versus add unsigned, where that unsigned, another better maybe name for it would be add with no overflow calculation, or add with don't care about if there's an overflow that results from that addition. Just return back whatever result you get in those equivalent number of bits, and that's up to software to figure out what's happening. Um, what we should do in the instance of overflow is not an easy thing to answer, right? What does it mean to have an overflow in my math? What does it mean for my actual correctness of my software code, be it the C code that we're generating assembly from, or just the assembly that we're writing ourselves? Is it has to be specified separately from the rest of the software specification that we have arithmetic, we're doing addition. What should we do when overflow gets detected? Uh, it's easy for me to say, but that's the main takeaway that it's not really clear. And so when I get those relatively low level questions about, well, if I have this and this, should there be an overflow and what should we do? Or is it okay if we use add versus add you for our assignments in this class? My answer is always, well, it's fine. It's okay. There's, for better or for worse, no scenario that I've put in front of you this semester in which correctly calculating overflow will lead to points getting taken off. Ultimately, I want you to show that you get the circuit correct for project part A. Here, it is a very simple circuit. Just show that it works. But when we look at those set less than unsigned instructions, and there was a question about that over the weekend. It's very subtle in terms of what should the correct result be when you have a set less than and there's an overflow. It's not clear to me. And if you look at the actual C specification that we're basing most of our assembly generation from, when there is overflow, it's intentionally left as undefined in the spec, meaning the compiler can do whatever it wants. Any result is valid if there's an overflow that is a result of your arithmetic. So from our perspective, we're starting from C code in which by spec, it's not necessarily don't care about overflow, but it's more about anything goes once there's an overflow scenario. It's hard for me to then turn around and say you must do exactly this when an overflow gets detected. So for our processor design, ultimately it will be a little flag that comes off our ALU. It'll be a single bit port that just says overflow, and it'll just kind of float out there, and it'll just kind of be a signal that you can test, and you can easily generate a test that will overflow, and it'll go high when that overflow gets detected, and then we don't worry about it again Because ultimately, just to reiterate here, it's just very dependent on what system that you're building from a software perspective. And it really depends. And so I can't say for certain for these sort of synthetic software examples we're building what the correct result for an overflowed operation should be. So the textbook definitely starts, certainly when you look at the appendix of, building up a 32-bit ALU and starting from a single bit ALU and staggering or staging the results from there. We already did that when we started our lab too, and you'll see a little bit of repetition when you're working on the projects that started last week, which is I do ask you to do a 1-bit ALU. I think it's a valid question to ask, you know, what is the right way to do it? And there is no necessarily right way. There's different design considerations that we have to trade off. There's the consideration of, well, how many lines of source code is it going to be in my VHDL when I do this design? The implication being that more lines of source code means it's more likely there's going to be a bug, right? The more lines you write, the more likely you're going to have a mistake somewhere in your code. We don't have, I believe, a good enough intuition collectively as a class to be able to truly say that this implementation strategy is going to be better than another from a hardware gates realization perspective or from a critical path perspective. In this week's topic, we'll talk a little bit about from the ALU designs how we can maybe improve upon our critical path, but it's still pretty hand wavy at this point, and it's going to remain that until really the end of the semester, until we try things out. And in this class, which is not a digital design class, that's a secondary consideration of this class, we feed the input to the tools, and the tools tell us what the critical path is. And one team's critical path will wind up being better than another team's at the end of the semester, and that's okay. And everyone gets full credit if their design works, and it's not a competition. Come take CPRE 480 with me, and we'll have some competitions along the way. Um, but that's a different class with a different clientele and a different philosophy behind it. So this is what I would actually kind of call the CPRE 281 approach to building a 1-bit ALU. And I'm not denigrating the approach. The approach is perfectly fine, but it is a different approach than what I would consider the CPRE 381 approach. We're building the same thing either way, but in the CPRE 281 approach, see if this is working here. No. And again, I don't want you to go back to your CPRE 281 instructor and said, Zambrino says that your approach isn't any good. I don't believe that. It's a different approach. It's an approach with a different pedagogical goal at the end of the day. I would argue that once you've learned the 281 approach, you'll never use it again in life. Uh, some would say the same about the 381 approach as well. So it's a relative thing. But the 281 approach is understanding the functions we're wanting to implement for a circuit and attempting to map that to all the things you learned in 281 about representation of Boolean circuits. So if we're building, and let's just say just a 1-bit ALU to start with, where we have an input A and an input B and I guess an operation, so our opcode or our ALU op, and we have our single bit output F here for this. The design was asking, can we build a single bit ALU to do both an AND operation as well as an OR operation? And the 281 approach is definitely let's build the truth table for that. That's what I would consider the 281 approach. Let's build a truth table for that, and let's figure out what that winds up being from a logic gates perspective. So we have 3 inputs and 1 output, so we know that there's just going to be 8 elements in that truth table. So we have an opcode, we have an input A and an input B. I like the 281 approach. It makes you feel pretty clever when you've got it kind of all figured out in the end. And it's a 1-bit opcode here, so we know there's a value that's either going to be a 0 for the opcode. And it doesn't matter what that can correspond to, but let's just say that corresponds to my OR operator. Or that value is going to be a 1, and that'll correspond to our AND operator. And then within that, we just have what our inputs are, right? And it can be that sort of binary pattern of 2-bit input and the 4 possible values it can be. And then we know what the result would be then accordingly. So if it's an OR operator, my output would look like that, right? Because if either A or B is 1, then my output is 1. And if it's a AND operator, my output is only 1 when both A and B are both set into 1. So that's what I would call the 281 approach, where we would take my inputs and treat this as a function that has a truth table associated with it, potentially a sum of products representation, and that's the kind of thing you would have learned in 281. How do I minimize this truth table? Well, you can start certainly with the sum of products representation, which is for every input combination that results in a 1 in my output, treat that as a separate term in my sum of products representation. If this only sounds slightly familiar, well, blame your 281 instructor, or remember that we're just showing this as an example to compare to sum of products, right? We have a bunch of a bunch of ANDed terms together, and we have a bunch of ORs of those, and it's a 2-level circuit corresponding to whatever function we're interested in. And in this case, okay, so we know that F is 1 when we have 0 for my opcode or operator, when we have 0 for A and we have B, or when the opcode is 0 and we have A is 1 and B is 0, or when we have 0 for my opcode and A is 1 and B is 1. I should put the little dots there to represent my little AND gates. Or when my opcode is 1 and A is 1 and B is 1, right? That's the 281 approach to building an ALU, in this case just the 1-bit ALU. Does K-map not sound familiar, that term? That's fine. Don't worry about it. We didn't do a K-map here. You could then take this circuit and then optimize it in using various different approaches. Just Boolean logic optimization, you can build a K-map and minimize the terms that are common. It doesn't matter. That's a 281 approach that then has a further optimization step applied to it. The 381 approach, which we're doing a little bit of a hybrid of both ultimately this semester, is in the 381 approach, we're just recognizing that we have different operators and we want to select between them depending on what we want the circuit to do. So it's the same functionality. It's not one is more correct than the other. But if we know that we want to build an ALU that has both an AND operator as well as an OR operator, um, all we would have to do would then just select between them. So we would have an input A and an input B, and we know we're potentially interested in ANDing them together. We're also potentially interested in ORing them together. And we're just going to have a mux, right? That has been our 381 philosophy. And technically, I made the operators backwards here in terms of which one was first and which one was second, but that doesn't really matter. And we have, instead of opcode being part of our logic that we're minimizing, our op is now just our select bit for a mux. To me, that's a cleaner way of reasoning about it. It becomes much easier to realize that now we want to add additional functionality, right? Maybe we also want as one of our operators, a half adder. Well, we just add one. Or we want to just invert A. We can just add those as inputs to our mux and expand our mux. Whereas if we go back to the 281 approach, well, now we're back to the drawing board. Now we're back to a larger truth table, having to re-optimize, re-minimize that circuit, or generate our sum of products representation. I believe, although it would take quite a bit of time to prove this from base principles, from a hardware realization perspective, just comparing the AND OR circuit here to the AND OR circuit here, I believe they're equivalent. I believe there are mux that can, the mux itself is also just gates, And the resulting operation is going to look a lot like this, that there's a value for when the mux input is 0 and a value for when the mux input is 1. And that corresponds to AND and OR gates anyway. And you wind up getting the same exact identical circuit back out. So it's a valid question. At what point does this approach tend to be more expensive? It's not clear to me in general if it's ever more expensive. And the 3-to-1 philosophy is designed for code readability and simplicity, and let the tools figure it out, right? Now, if we were to compare this to, and this is a very small preview, maybe it's not even a good preview. I got to be careful about this. The 480 approach. This applies to other classes as well. I'll call this. I won't take full credit for it. I'll call it the 480/488 approach. Um, you probably don't want to take both next semester if you're interested in it. Take one, and then if you're a junior, save the other one for spring of your senior year. They're both good classes. I created them both. My imprint is on both of them. The 480/488 approach is also fundamentally different than that, which is drag and drop an ALU IP core. That sounds even easier, right? It's not, because certainly when you drag and drop that ALU IP core, now you're no longer designing from a source level perspective. That ALU IP core is going to have 7,000 different parameters you're going to have to understand, and you have to understand it at a deep enough level. So instead of staring at tens of pages of VHDL source code, you're looking at hundreds of pages of PDFs to understand the components that you're using and how they all play with each other and how to interface them all together. And that's very much both in 480 and 488 the approach we use. What I can certainly say is it's pretty clear to me the main advantage as we go from sophomore level approach to junior level approach to senior level approach is productivity definitely increases as you go. Again, from a circuit perspective, I think they're going to be very similar to each other. Even this approach with 7,000 options, well, if you select the exact right options, you'll get this circuit back out or something very similar, comparable to it. But when you're dealing with this, there's only so many gates you can generate in a day, right? I mean, the more you try to do, the more likely you'll introduce a bug along the way. And even if the circuit is resulting the same, you're operating at a pretty low level, and you're caring a lot about should there be a gate here or a gate there. The 381 approach is essentially what data has to route through my circuit, what size mux do I need, how do I control the inputs to that mux, and you're more productive than in the 281 approach. Now, when you get to the senior level approach, the 480/488 approach, now it's what IP cores do I need in my system? How do I interconnect those together? So productivity definitely would go up in terms of what kind of demos can you do, right? The 281 demo probably is also pretty fun from an FPGA board perspective. We'd be able to demo a whole lot more if we went down that path in 381, right? We're building a processor that is very close to being able to run a whole operating system on it. Not quite there. It's extremely close though, and we haven't learned operating systems yet anyway. Um, and then in 480, 488, now you're building something that is a real approximation of real world cutting edge hardware that you're building in those labs, and you're able to be that much more productive based on what the tools are providing for you. But there's disadvantages, as well. You get less and less of a view of the low level internals of the system as you go to that higher level of abstraction. Anyway, so our approach this semester in this class, that's what you should care about today, is a little bit of both. We sometimes drop back down to that 281 approach if we're trying to understand things like how overflow gets calculated. But the 381 approach, both for just designing our ALU, um, as well as for interfacing with all the functional units in my system, is where we find that sweet spot this semester. Goes back to that fundamental question of, since that is our approach, why are we designing a single bit ALU in the first place? And I think that's a valid question, because that's how the textbook does it. Because the other corollary of the 381 approach, I'll have something to say about this in a minute, is why even do a 1-bit ALU at all? And I think that's a valid question. I'm going to try to come up with an answer to that as I draw this. That instead of this single bit ALU that we've created, Why not just do this entire design, which we now know how to do? And if I had asked you to do it this way, this design should look extremely similar to the one above. Why build up from a 1-bit ALU at all? That would be a 32-bit AND gate, which we would know how to build, a 32-bit OR gate, and then either a data flow or other 32-bit adder, and then just mux those results. The honest answer is that's probably also a valid approach to take for this class. It's just not the approach we have. So um, I always have to be a little careful when someone asks me that. Say, well, can't the question would be, well, can't I just build the 32-bit ALU and skip the 1-bit ALU part? The answer is yes, your design will work, but you will lose points because the assignment says to build a 1-bit ALU first and then to stagger them together to make a 32-bit ALU. It's not a very satisfying answer. Um, that is the answer at this point in the semester that we're dealing with. It's not that much harder, and I think we've already seen that, right? We've overcome our generate loop headaches, and they're no different now than they were back in Lab 2 in the second week of the semester. That, yes, this is definitely going to be significantly fewer lines of code and files and things like that. But once you have gone through and built this, making a 32-bit version of that is really straightforward. We know how to do that. Right, and this is a 32-bit N to 1 mux versus a 1-bit N to 1 mux. It doesn't really matter whether it's a single bit mux or it's an N bit mux. It's the same amount of muxes, right? There is no actual N bit mux, right? It's just N of those 1-bit muxes kind of near each other, adjacent to each other in my diagram. You wind up getting the same exact circuit back out. My answer is always carefully read what the assignment says for what we need to build for this project. But philosophically, this approach is probably even a little bit superior to this approach here. Reasoning about the behavior of what my circuit needs to do and using muxes as my control gates versus dropping down to single bit level operations. It's just going to be a lot more efficient of a design at the end of the day. We're getting a little bit off target here. I think the most important takeaway from that though is that there is no single best way to build something like an ALU. In fact, I think we tend to think of adder design, for example, as kind of a solved problem. We know how to build an adder. It's not that clear at all that we know how to build an adder. Not as a class, but as a community of engineering professionals in this broad field of computer architecture. It is still an open problem of what is the best adder design for a given scenario. It is still on the critical path of all modern microprocessors, and usually it's floating point people are caring more about now than the integer math that we're doing this semester, but that is still a very much open question. How do I get my add operations, and usually it's multiply accumulate operations, but how do I get my multiply and add operations as efficiently, as effectively as possible in a circuit? It's still very much an open design question. And so while we don't want to necessarily belabor the point about the 281 approach versus the 381 approach, even from within the 381 approach, we have one example adder that we build in the lab. And the main reason we build that adder is because it is the easiest one to build, the most straightforward, the adder that corresponds to the elementary school math of bit serial addition and then propagate the carry bits so that we can get to the next bit of addition. That is the main design criteria that we have in this class. Let's get through these labs. Let's get something that's tractable and doable in a reasonable period of time. It's not at all clear, both in this class as well as in the world at large. What is the best way of doing an add operation? Modern microprocessor design, certainly on the GPU side, and that would be a small advertisement for CPRE 482 maybe next fall. A big part of modern architectures for machine learning, certainly on the GPU side, are all about how do I most effectively pack as many add circuits into my design as possible. And when you have to worry about that, and when the answer is in the tens of thousands at the end of the day, the number of adders you have, uh, shaving off a little bit of efficiency becomes very much worthwhile. Separate question from John. We're jumping around, which is fine, because I know we're talking about lab stuff here. For the barrel shifter, do we need to provide protection against an SLA operation? I have to chew on that a little bit. Um, That would be for a shift left arithmetic, which there is no instruction for it. And we talked about it very briefly, like week one of the semester, or maybe early week two of the semester, that there is no shift left arithmetic instruction because when we shift left logically, we're automatically shifting left arithmetically. In fact, it may be a valid pseudo instruction, I don't know, because it's the same exact operation. When we're shifting to the right, we have to potentially pay attention to that sign bit. The idea being that if it's a negative number and we're trying to effectively divide by that, my hands are up, but you can't see them in the camera. We're trying to divide by that power of 2, that sign bit is valuable for us. If we go from -8 and we want to divide by 2, the result should be -4 and not something that now is unsigned. When we're shifting left, there's no consideration for that. Unless you mean if by shifting left, do we overflow? And no, we don't have to worry about that. So maybe from that perspective, that question makes sense. If we shift to left so much that we go from a negative number to a positive number because we've shifted out the sign bit, that's the spec. That's what it's supposed to do. So um, you don't have to actually worry about that in your design. Okay, so this general ripple carry design, this textbook design, is something we've already built, and it hasn't really changed. We built one that did kind of add slash sub, and now the only difference as you move on to your project part A designs is it's got that internal mux that's doing potentially more things. And the assignment specifies what those things are supposed to be. And if I was a real jerk and I said, this week I'm going to add a new operator to your project part A design, that wouldn't be very nice to me, but I reserve the right to do so. It'd be a very straightforward thing to do. It would be, okay, we have an and an or, and if I decide, well, I really like X nor or something like that, I don't know. It would just be an additional input. Extending the mux potentially. Muxes tend to go at those powers of 2. So this is a 3 to 1 mux. So you already have the right number of bits for your control, your select lines for your mux there, and it would just be adding an additional input to your mux. And that philosophy is why we like the 381 philosophy. It applies to everything that we're using with this mux-based control mechanism, which is let's add an additional instruction to a design that's already working. It tends to be looking at our current architecture, our diagram generally, and determining what signals need to be muxed out and changed based on what that new instruction is supposed to be doing. So this applies for our ripple carry design, even though as we look at that carry path, this black line going from carry in to final kind of carry out at the very end, that carry path is really only relevant in the context of the adder part of that circuit. The AND gate and the OR gate don't engage the carry path at all, and those should all be zeros then for your for the design that's coming back out. Um, but another way to think about this though is my circuit doing an AND, an or an addition operation? And with this mux-based control mechanism we do this semester, the answer is yes. We're always doing all three. My operation is always doing it. My ALU is always doing an AND. It's always doing an OR, and it's always doing an add. So you can think of it as we built 3 little ALUs potentially. And then we're selecting which of those results we actually want back out at the end of the day. And this is the 2's complement approach. We did already for lab 2. It's no different. The idea being that to do A minus B, we can do so via negating B and then just adding them together. And we do the 1's complement, which is literally just inverting that value of B. And then we also have to then trigger the carry in bit as well. That part of your design for project part A should be identical to what it was for lab number 2. And that's okay. If you didn't get that working for lab number 2, here's your chance to get that working. That to support that operator of subtraction, you would do so via negating B to get the 1's complement, and then adding that +1 to your design to make it a 2's complement. And then you wind up with A plus negative B to get your A minus B result. This does give the impression that it's an entirely separate control input. And likewise, as we try to get a little bit clever and maybe use De Morgan's law, going back to 281 here, to to get other circuits kind of sort of for free here. Um, that scheme is still entirely up to you, and I think that's the nice part about this. That technically, this single bit signal is being used to drive a mux that is selecting between an inverted value of B or not, and we likewise now would have one potentially for inverting A or not. But at the end of the day, perhaps there was 2 bits to connect to this mux here, then one additional bit, then one more additional bit. You would just have a 4-bit select line or a 4-bit ALU op input for your ALU to be able to support all those different types of operations. The idea behind being able to also invert A is it allows us to implement functions more in the 281 style of things here, right? Where we can then say, lost my stream here for a minute, 1 second. Okay. Where that if we wanted to implement A nor B, the 281 approach says, if you're interested in implementing A nor B, you can use this old chestnut of the equivalent circuit not A ANDed with not B. In the 281 approach, that's very clever of us. That by doing so, and just by controlling for a mux that inverts A and also inverts B, we can use this AND gate and now get a NOR operation back out. An equally valid 381 approach, what would be what? If we wanted to do a NOR approach for 381, let me phrase that a little bit more clearly. If we wanted to add the NOR operator to this ALU using the 281 approach, we would use like De Morgan's law and be clever with our input inverting. In the 381 approach, what would we do if we also wanted to support the NOR operator with this current ALU design? Yep, just add a gate. Don't overthink it, right? And I'm going to draw it, and it's going to look ugly, but that's okay. We realize, oh well, we can just draw it down here. We don't have to draw it in the middle there. That we also want to support the NOR operator, and I'm not going to draw all the connections for it. And again, it's a little bit of hand wavy when I tell you that it's an equivalent circuit to what the 281 approach would get you. This is adding, well, it's adding a couple things, right? It's adding an additional explicit gate as well as an additional input to your mux. So eventually, as you add more inputs to your mux, your mux requires more logic as well. The quote unquote 281 approach is also adding circuitry for the mux as well as circuitry for that explicit inverter. If it's not exactly equivalent in terms of number of gates, um, it's going to be very, very similar. And someone was joking, say, well, it's all NAND gates at the end of the day. Even that we can't say for certain, right? As we're doing our FPGA-based synthesis, which we'll get back to on Friday once I get my camera thing to work correctly. Um, as we're doing our FPGA-based design methodology, it's actually not NAND gates at the end of the day. It's lookup tables at the end of the day. I don't think we'll spend a lot of time talking about that. We'll see them. We'll actually explore the FPGA chip and see what they look like. But from the lookup tables perspective, AND gate, OR gate, NAND gate, it doesn't matter. It's all the same. It's all a truth table that gets directly encoded into my circuit. So it should be very, very similar when we're mapping to an FPGA at least. And even if we weren't, if we were doing explicit gate-based logic minimization, it should be really, really close, if not identical, when the synthesis tools get their hands on it. What can be little tricky, and I think it's in part based on how um, the instruction is defined and how it's explained in the book, is we are going to use this ALU to also support a set on less than instruction. And I would say we are doing so using the 281 approach. Um, because certainly in the pure 381 approach, the approach I'm saying you're not really allowed to do, there's literally nothing stopping you from adding that to your circuit. That would be valid as well. A less than operator in VHDL is not some free special thing. It's implying a subtractor circuit anyway. So it is going to ultimately be equivalent logic we're doing here as well. But in the 281 approach, what we do is we take that understanding of what the set less than arithmetic instruction is supposed to be doing, and we output the equivalent result back out. So this phrasing is closer to the green card phrasing of what it is trying to doing. But set less than is an arithmetic instruction, and if we remember what it looks like in our actual MIPS syntax here, we are using it typically because we want to do a branch equal or a branch not equal afterwards. But so if we have our set less than, and for that purpose, let's use our assembler temporary, although it doesn't need to be that, two other random registers. The pseudocode for that, right, is if T2 is less than T3, then that value of AT is set to 1. Else it's set to 0. That's the pseudocode for it. We're not actually implementing branches and things like that in our logic implementation. And when I say that AT is set to 1, what can be a little confusing when you're implementing that is I literally mean the value of 1. So if we were to look at the actual AT register, it would have a value of 1 in the least significant bit, and those other bits would always be 0. Likewise, if the result is 0, well, then we know what that looks like. All the bits would then be 0. So in terms of implementing this set less than operand, uh, this is probably closer to the 281 approach here. We have to recognize that for all of those most significant bits, from bit 31 down to bit 1, I could have drawn another 0 here to make it more equivalent. For bit 31 down to bit 1, the result of a set less than instruction, or the operand in our operation in our ALU, is always 0. So from that perspective, when we're implementing set less than using our 381 approach here, the output for my set less than operand, and my poor mux needs to get extended here, but that's okay, we'll squeeze all those values in. For all those bits, save for the least significant bit of my ALU, the result of the set less than operation is always 0. So far so good, right? So for 31 of my 32 bits of my bit sliced ALU, the value is 0. And so we still have to have some way to specify that, but we do have that nice optimization available to us there, that it's always 0. It's only the least significant bit. So this would be a design for kind of bit n. If it were to be bit 0, then we do need to have some input to the circuit that specifies that this is less than, that the result of a comparison was less than. And there are a lot of different ways one can do it, but the basic textbook idea, which is what I would like for you to implement in the lab, is to treat it as a subtraction operation. So we have our n-bit ALU, and this is an example of looking at the most significant bit. This is bit 31 of your ALU. So already in lab 2, for many of you, you treated the most significant bit slightly differently. You didn't have to, but many of you did. Certainly now for the project part A ALU, you definitely do have to treat that most significant bit as a slightly different component with slightly different logic going on there. And part of that would be um, for that set operation, and also for overflow as well. But the general idea for that is we can treat our set less than operation as a subtraction operation. And we can go back to our pseudocode for that purpose, which is saying if T2 is less than T3, and we're basically replacing that with if T2 minus T3, let's put some parentheses there, is less than 0. I know what some of you are thinking. Well, there's a lot of other ways I can do it. There are other ways one can do it. You're safe in following the textbook approach for that. So if the A is less than B is the same as taking A minus B and determining if the result is negative or not. This is why set less than unsigned becomes a little problematic to me. But for our purposes, we start with this assumption. A less than B is the same as taking A minus B. and determining if the result is negative or not. And another way we know that determining if something is negative or not is also saying take the value of T2 minus T3, and this is a completely arbitrary pseudocode notation I'm just making up as I go here, bit 31 of that, the most significant bit of that, right? We want to know if it's less than 0. That's what the sign bit tells us. Was the result less than 0 or not? We can use the sign bit for that. So take T2 minus T3 and check the sign bit for that. Likewise, we know all these other bits are always 0. This least significant bit is going to be 1 only if the result of subtraction was negative. So another way to specify what this instruction is doing is it's specifying that of my result, bit 0, I'm not going to draw it again, is equal to that operation. That's really sloppy looking at my part. But that conceptually, that's what we're doing here, right? Checking if we're setting only bit 0 ultimately, and we're setting it based on if the result of the subtraction is negative or not. And that would be the most straightforward way to implement your set less than operation. You would use the same exact adder, and you would just have a little bit of extra care now, and you can see the actual connections happening here, that for input, for this output of the actual add operation, we're now using it for two purposes, only in that most significant bit of our adder. We're using it potentially because we may just want to have done an add or subtract operation, and now we're also using that bit, and we're going to call it set. Or you could also have called it result of subtraction or result of operation is negative. It depends how literal you want to be. We're only using it for set less than, but that's what that bit is specifying. Is the result of whatever we added together negative or not? Because that's only in that most significant bit that we're doing that here. And then now we're adding an additional input to our muxes for all of our ALU bits, which we're calling less than or calling less. Again, that is the same as what I was drawing over here as well. An additional bit that for almost all of these is a 0, but for that least significant bit is potentially a 1 or a 0. And then finally, what we get for our 32-bit mux, our 32-bit ALU, is a design in which there's a little bit of an additional feedback loop than what there was before. We have still our carry chain to support our adds. We have our opcode, however you want to encode this. The book explicitly has A invert and B invert. You can just have a big mux. That's also fine for your 1-bit ALU. And then now to support explicitly that set less than operation, we have an additional input to each ALU bit called less than, whatever you want to call it. Which for all these other bits, if it's a less than operation, the result is always 0. Again, don't overthink that. Look back to this slide when you're designing this, that no matter what, the result of the less than operation is either binary 1 or just binary 0. So all those other bits are always going to be 0 no matter what. So we can actually hard code that in our design. For all these other bits, if it's a set less than operator, we know what the result is, it's a 0. It's only for that least significant bit that is either potentially a 1 or a 0, depending on what the result of the subtraction operation was. And that's what we're grabbing from that most significant bit. You could call that signal set, as they do in the design for the textbook. Call it result of an add operation was negative, and that's what we're connecting back into that least significant bit for our ALU there. This is actually a pretty good stopping point for us. And what we can do on Wednesday is now go beyond what the textbook talks about and talk about some extensions to this ALU that are brought up both in Homework 5 as well as in Project Part A as kind of optional things to work on. And look at how we can adapt this design to support the so-called SIMD mode of operation. Hopefully this helps as you're working on the project. Think in that 381 style of things, but also follow the instructions, even if that's somewhat contradictory at points as you're working on it this week. Otherwise, good luck on things, and I look forward to seeing everyone on Wednesday.